So, in the previous lecture we have introduced the concept of countable sets and few examples we have seen the countable sets or uncountable sets. Here we will continue with the same countable sets with few more examples. So, the first example let us say set of all squares of natural numbers has a number is countable because the set of squares of natural number means it is 1, 4, 9, 16 and so on. That is a set of those element x where x is of the form n square and n is a natural number. Okay. So, this set has a one-to-one correspondence if we define a mapping f from J to this set say capital A, which maps n to n square, that is f of n is n square, then it is easy to show that f is 1 1 and it has a one-to-one correspondence. So, because why 1 1? Because f n 1 equal to f n 2 will implies n 1 square minus n 2 square is 0, which implies n 1 minus n 2 into n 1 plus n 2 is 0, but n 1 plus n 2 cannot be 0. So, this implies that n 1 is equal to n 2. So, f is 1 1. Therefore, there is a one-to-one correspondence between the set A and set of positive integers j 1 to n and so on. Hence, A is countable. Similarly, the other sets are also like set of all even positive integers or set of all odd positive integers or maybe the set of all prime numbers, that is 2, 3, 5, 7, 11 and so on. These are all countable sets. Which can be easily shown by drawing a mapping from this set to the set of natural number, which is easy to just say. Even in positive integer f of n is equal to a mapping can be defined from J to this set say B such that f of n is equal to 2n. Then this is a 1 1 mapping and into. Similarly, here odd integers 2n plus 1 and like this. Similarly, for the primes also we can do for that. Okay. So, these are all sets which are countable and it is all subsets of a natural number, subset of the. So, it means this shows that an infinite set is a set which has a one-to-one correspondence with its subsets also. Okay. So, that is why we define like that. Then another examples which we are doing, the set of all rational numbers are countable. Set of all rational numbers is a countable set, and this also we have discussed it that when the positive, let us take the different cases here again. Suppose I take set of all positive rational numbers, that is, it will be of the form p by q, where p and q both are positive. Okay. So, basically this and p q are say integer natural numbers. So, basically this is of the form, if you put it in the form of the sequence, it is of this type p q sequence, where p q are natural number. Then we can arrange in the form of the sequence, we can arrange these numbers in the form of sequence such that p plus q is r, where r is 2, 3, 4 and so on. It means we can put it in this way 1 by 1, the first term, so that p plus 1 is equal to 2. Then we can put it as another say 1 by 2, 2 by 1, so the 3, and then we can go 1 by 3, 2 by 2, then 3 by 1 and continue this. So, it has a 1-to-1 correspondence with the set of positive integer, which has a 1-to-1 correspondence with the set of positive integer 1, 2, 3, 4 and so on. So, it is a countable set. Then same case is with the set of all negative rational numbers. In a similar way, we can, it is also countable. Then, so it is this is countable, is it not? And this, then set 0, singleton set 0 is a countable set, is a finite. So, if I take the all union, then set of rational number is set of all positive rational numbers, all negative rational numbers and including 0. So, if we put it in this form 0, 1, minus 1, half, minus half, 2, minus 2 and continue this way, plus minus and all these things, then this entire set is countable. 1-to-1 correspondence with that and countable. We can get this. Then also we were discussing about the points whose coordinates are rational number. This is another example that also we have seen. The set of points in a plane whose coordinates are rational numbers. Is countable. So, set of points in a plane whose coordinates are rational numbers, that is the set is of this type whose coordinates are rational numbers. So, we can say A B, where A and B both are rational numbers. Q is the set of rational numbers, because any point in the plane will be ordered pair and we get this point. Now, this is each Q, since Q is countable, Q is countable set, and this set is a ordered pair of whose elements are countable. Then according to that result which we have seen, that if S1, S2, Sn are countable, then the countable union of the countable set is countable, and accordingly we can say if there is a n tuples, each coordinates belongs to a set which is countable, then that collection of the n tuples will also be countable. So, basically it is a double means coordinate, and where these are rational. So, this will be a countable set, is it not? So, we can say it is a countable. Actually, based on this result is that set of point based, since you can say the set of points in p dimension, this is dimension is 2. in p dimensions, each coordinate of which which assumes a countable set of values is countable. In fact, this was shown already, because if suppose a set of p dimensional is there, we prove by means of induction. We have shown that if the set this set A1, A2, AP, where the AI's are in a set A which is countable, then this collection of the set is also countable, and this we have shown when I is 1, then this coincide with the set A which is countable. Then we have assumed for p say up to p minus 1, and for the p, when you write the point, it is of this form called ordered pair. Then when you fix up one value, other values keep on changing. So, it is a countable set. So, this we have already discussed, and this countable. Okay. Now, based on the another result, which is the set of polynomials that is a naught x to the power n plus a 1 x n minus 1 plus a n minus 1 x plus a n. This is the y, where the coefficients, this set of all polynomials, where the coefficients are integral coefficient with integral coefficients is countable. Means this set of polynomials where the coefficients are integers is countable. Now, you see there is a one-to-one correspondence between the set of polynomials and this set of p tuples, since there is a one-to-one correspondence with the set of points correspondence between the polynomial a naught x to the power n, a 1 x n minus 1 plus a n, let us be p x of degree n, to the tuples a naught, a 1, a 2, n plus 1 tuples. There is one, means corresponding to each polynomial we can get these tuples, and if this tuple is known, we can construct a polynomial of degree n. So, there is a one-to-one correspondence between these two. But what are the coordinates? But the coordinates of this, they are integers, integral values, and this integer is a countable set, which is countable. So, this collection of the tuples is countable set, because these integers and this collection of the tuples will be countable. So, this is countable, and there is a one-to-one correspondence between the elements of this set to this. So, this collection will also be countable. So, this shows that set is countable. So, set of polynomials is countable of degree say n is countable. It's okay. Then algebraic numbers. The set of all algebraic numbers, the set of all algebraic numbers is countable. What is algebraic number? The algebraic number x it is a solution of an algebraic equation. The an algebraic number x, an algebraic number x is the solution of an algebraic equation of the form a naught x to the power n a 1 x n minus 1 plus a n equal to 0, where the coefficients a naught, a 1, a 2, a n, these are all integers. So, this is the solution. A number x which satisfy this equation will be an algebraic number, or corresponding to a solution of this equation will be an algebraic numbers. Now, if we remove this 0, just I take, then this is a polynomial of degree n, and the coefficients are integers. So, according to the previous result, if the coefficients are integer, then collection of all such polynomials will be a countable set. Clear? So, once the polynomial, when we put it equal to 0, you are getting an algebraic equation. So, the roots of this algebraic equation will be at the most n. So, these n roots which will satisfy this equation. So, each equation will have the roots, and since this equation, this collection of the polynomial is countable, therefore, the corresponding roots will also, set of all algebraic numbers which are the roots of this equation will be countable. So, this we can say like this, we can write like this, since every polynomial equated to 0 has only a finite number of roots. Has only a finite number of roots. Therefore, the set of all algebraic numbers, the set of all algebraic numbers forms a countable set countable sets of finite sets, because these are solutions are finite. So, it forms a finite set. So, it is countable and is consequently countable, and hence is countable. Consequently countable. That is what, because this polynomial, when you find the roots of this polynomial, you are getting a finite roots, maybe at the most n. So, basically each equation correspond to a roots. So, we can just say that this equation has the roots, say alpha 1, alpha 2, alpha n, say alpha 1, alpha 2, alpha p, where the p may be less than or equal to n. So, this equation will correspond to this. So, the collection of all such equation means collection of all such elements, but these are finite, which is countable, okay, and then collection pth tuple is also countable. So, this set will be a countable set. Okay. So, okay. Then the algebraic numbers, once you get, then all the transcendental numbers becomes the uncountable. So, let us see the few examples of uncountable sets. First example, which is say very important, is the real set of all real number in the interval open interval 0 1 is not countable. is not countable. So, what the concept is that all the infinite sets need not be countable. So, this is one of the example where the set of all real numbers, these are they form infinite sets, infinite real numbers lying between 0 and 1, but this set is not countable. The reason is like this. We assume suppose the set is countable. Suppose the set of all real numbers, suppose the set of all real numbers in the open interval 0 1 is countable. So, once it is countable, we can arrange in the form of sequence. So, we can arrange them in the form of sequence. We can arrange the elements of this set in the form of sequence. Say suppose say x 1, x 2, x n and so on, because they are infinite numbers. So, we get a sequence, infinite sequence. Okay. Now, each x I, these are reals in the interval 0 1. So, we can write down the decimal expansion of x. So, each element, each x I will have decimal or can be expressed in a decimal expansion. Decimal expansion will have a decimal, can be expressed, will have a decimal expansion or can be expressed by means of can be expressed in terms of the decimal expansion, in decimal expansion. So, let us suppose the x n is having the decimal expansion as 0.a1n, a2n, a3n, ann and so on, where what is a, where these coordinates, where the age, these age and these age are any one of the integer or any one of the digits 0, 1, 2 up to 9, a terminating, we assume is a terminating decimal being terminating decimal being supposed to end with a continuation of zeros. Means when the terminate, suppose it terminate here, then rest we will write 0 0 0 0 like that. So, it terminate 1. Okay. Now, with the help of this, let us construct a new number. So, now we construct a number alpha as follows. Alpha, I am writing the decimal expansion of alpha is 0 point alpha 1, alpha 2, alpha 3, alpha n and so on, where such that the alpha n is nothing but a n n plus 1, except that a n is 0, alpha n is 0, when a n n is either 8 or 9, in order to avoid the possibility of recurring 9 in it. This is done in order to avoid the possibility possibility of a recurring 9 okay, in alpha. This we are doing. Now, we claim that this point alpha so constructed differs from each any term x 1, x 2, x n of the set of the points in the 0 1. Why? At least at one place. Suppose I take x 1, then x 1 here is a 1 1 is the first place, a 1 1, while the in alpha the first point is alpha 1 and alpha 1 is what? A 1 1 plus 1. So, basically whatever the first point is, first decimal place is there, we are replacing this by plus 1. Next digit, the digit will be, say, instead of this we can write the 7 to 8, 6 to 7 and so on, except on whenever it is 8 or 9, then we can write this to be 0, that is all. Suppose this is 8, then we get 9. So, we will put it alpha 1 to be 0. Similarly, when to x 2, the second decimal place in x 2 is a to n, but second decimal place of alpha is alpha 2, which is a 2 2 plus 1. So, again 1 is added here. So, clearly we will see except. So, this number alpha is different from any one of the numbers x n. For it is different from x 1, in at least the first digit. It is different from x 2 in at least the second digit and so on. So, this way. So, but alpha is what? Alpha is having decimal expansion where the positive this side is 0, means all the terms are less than 1, lying between 0 and 1. So, it is, but alpha is a real number lying in the interval 0 1, and since we have assumed 0 1, the set of all real numbers in 0 1 is countable. So, it can be arranged in the form of a sequence that we have, but this alpha does not fall in any one of the does not coincide with any one of these x n. It means that our assumption is wrong, because if it is countable, then alpha must be one of the x n's, but this is not true. So, that shows that our assumption is wrong. So, contradict our assumption, hence 0 1 set of all points, hence the set of all points, all real numbers in the interval 0 1 is uncountable, is not countable, and that is proof. So, okay. Now, if we take, say, any interval, the set of real numbers in any interval a b is not countable, because if I make the function t minus a over b minus a, this is our f t, then it will transfer the function, this mapping will transfer the interval a b into the interval 0 1. Okay. And this is a 1-1 transformation, it is a 1-1 mapping. So, and this interval is uncountable. So, set of all points in this interval is set of all reals, in this interval is uncountable. So, in this also set of all real numbers in this interval is uncountable. And then if we extend it, then we say an important result is that is the set of the continuum is not countable. The continuum is not countable. Continuum means set of all real numbers over entire real line is not countable. Entire real line is not countable. That is what it. As a corollary of this, we can prove one thing: the set of irrational numbers in any interval is not countable. And solution is very, because a interval a b contains both rational and irrational points and irrational real numbers, reals. So, and rationals are countable. This we have seen. This is uncountable. Therefore, this implies that set of all irrational numbers in the interval a b is not countable. And same way we can also write this corollary: the set of transcendental number, which are not algebraic numbers, transcendental numbers in any interval is not countable. Because the reason is, if we remove the set of all algebraic numbers from this, then we obtained a algebraic number which is countable. We can get the transcendental left out, because the reason, if we remove the set of algebraic numbers which is countable, from the any interval a b, then the complement set of transcendental is non-countable, is uncountable. Then complement of it, then remaining one, which is transcendental number, will be not countable. And that is one. Okay. So, there are few examples we have seen. Now, few more we will continue when we go for the concepts of like some dense set, then perfect sets, etc. Then we will go for the few more examples where the countability or uncountability of the set is will be considered.